Okay, so this is a continuation. This is video 2 of class 13 in fluid mechanics, and we are in chapter 6 of Sengel, and we've just done Reynolds transport theorem, and we resulted in this equation right here. This is for steady flow situations, where we're going to generate this thrust. It might be from a jet engine, or it might be from a rocket, or it might be from runaway hose right here. And we saw a little video clip in class of the movie Roxanne, where we're doing the fighting training. Here is the example we'll do, the first example of maybe too many. I don't know if I'll be able to do all the videos for these examples, but I'll try. And well, we have, of course, not a hose here. This is an elbow. It's much larger than a hose, and this is a pipe right here with a pressure gauge, and this is reducing down. And we have a mass flow of 14 kilograms per second on the horizontal pipe here, and it's accelerating this fluid, and it's going up at a 30-degree right here. So the inlet is 200 millimeters, and the outlet is 30 millimeters diameter, and the elevation change is about 300 millimeters right here. The mass of the elbow is 35 kilograms, and the inner volume of this is 6 e to the 3, right? So 6/1000ths of a cubic meter. We want to determine the pressure at this in this pipe, and that we need to want to find the anchoring force that holds the elbow in place. So we're also going to assume this momentum flux correction factor is 1.03. Quite often we'll just ignore it, but that's okay. All right, so start with some preliminary stuff. I'll get the areas of each of these right here. So pi over 4 times 0.2 squared. All right, so that's 200 millimeters. That's why. So it's 3.142 e minus 2 meters squared. Same thing here, but we're going to go with 0.03 squared, because it's 30 millimeters, and that's 7.069 e minus 4 square meters. So they give us the mass flow rate. So let's get the volumetric flow rate. Is going to be the mass flow rate divided by density. And so that's 14. And we're going to divide by 999. We should probably just do an approximation and make it equal to 1,000. But I have it written down this other way. So whatever. And that's to the minus 2. So we get cubic meters per second. So that's going to let us get the velocity at, not volume, that's a volume symbol. Only get velocity, whoops, come back here. The velocity one is going to be the volumetric flow rate divided by the area. And V at 2, same thing. Volumetric flow rate divided by the area at 2. And you could do that in your head. I mean, you could do that on your own, probably not in your head. I couldn't do it in my head. But we can just go ahead and write that down as if we wrote it down, right? So save ourselves a little bit of time. So we have that set up. We want to first get the pressure right here. They asked for the pressure, they determine the pressure. But we would need to find it anyway for the anchoring force, so just be aware. And so to do that, we're going to use Bernoulli, our good friend Bernoulli. And so as part of that, we're going to have to make some assumptions. We're going to do it along a streamline. It's going to be incompressible. Well, it's water, so that's pretty standard to assume. And it's going to be steady flow. Did I say that already? And we're going to ignore viscous forces. So we take P1, where we're going to let's call that right there 1, and let's call that right there 2. Right? I guess we already did because we got the areas and the velocities, whatever. So we get plus 1/2 rho v1 squared plus gamma z1 is going to be equal to P2 plus 1/2 rho v2 squared plus gamma z2. Let's call this the datum. So this is the datum, so that's where it goes to 0. And let's call this one atmospheric. Right here, because that atmospheric right there. So we're going to find this is going to end up being a gauge pressure because of that. And so we put the numbers in 999, and our inlet is 2.242 squared. Right? It's going to be equal to 1/2 999, but now 19.83 squared, and then the gamma is 9,800 newtons per cubic meter, and we're going to go up 0.3 meters. So if you want to find out what the in-between values are here, what's driving this right here, we have 2,511, 196,400, and then this is 2,940. So this, the vast majority, is that dynamic pressure. So P1 must be 196,800. And these are newtons per meter squared as a pressure. And for our information, that's 196.8 kilopascals. And of course, it's a lot easier to get our head wrapped around this if we could compare that to something. We know that atmospheric's like 101.4 kilopascals. So this is 2 times that. We also know that atmospheric pressure is 14.7. So this is sort of almost like nearly 30 psi. Like how much pressure is in your tire is how much needs to be right in here in order to create that volumetric flow rate that we found, right? That mass flow rate they gave us. Other things I want to find out is I want to find out how much the water weighs inside this this elbow. This is an elbow, not a nozzle, but it looks like a nozzle. Gamma times the volume, so that's 9,800, and times 6e minus 3, so that's 58.80 newtons, right? That's the volume, there's the specific weight. And we also want to know of the elbow. We were told the mass, so we want to get the actual weight of it. So it's 35 kilograms times the acceleration of gravity, and that ends up being 343.4 newtons. Now for the momentum analysis of the thing, I want to get these forces, so I'm going to draw an FBD, and I'm going to make a momentum diagram. And on the FBD on the thing, right, so remember for this, we're actually making a control volume. We'll kind of draw the control volume onto this right there. And we're going to have the forces acting on here. I'm going to draw them in the positive direction. So these are reaction forces that are going to be of the holder, or let's see what it says, determine the anchoring forces needed, right? So these are going to be the anchoring forces. Rx being applied to right there. Over here, because we drew an FBD, and the most important word in the FBD is the F, right? So the free of the free body, we had to cut it right here to make the thing free, and by doing so, there's actually the pressure inside the pipe acting onto this. So the force is going to be P1 times A1. That's acting onto the control volume. We also have the weight, and then right next to it, we can put the weight of the elbow and the weight of the water and the weight of the elbow. And if somebody asked, yes, it's actually at the same spot. I just wanted to put 2 arrows on it, so it's not going to matter. I just put them separate right there. On the momentum diagram, draw this thing out here. I'm going to draw the control volumes kind of into there. Here are the control surfaces, though, right? And the control surfaces is what we care about. And we're going to have a velocity coming in here, and we have a mass flow and velocity 1. And we're going to have mass flow and velocity 2 coming out. And remember that this is 30 degrees. I guess I'll put a theta in there. Why not? So the main equation we're using, I like to put the main equations before we go to the individual parts of the thing. We know that's going to be the beta mass flow velocity out minus beta m dot velocity in. So we get the x direction. The forces acting onto this. I have Rx, which is what I want to find, plus P1A1. They're in a positive direction. Nothing else in the horizontal direction acting onto this. I'm going to have beta times m dot times V2, because that's the outlet right there. But in the x direction, it's only times the cosine of theta. And now we're going to have the entrance into here, and so we're going to have our beta times our m dot V1. So let's put our values in here, and the pressure is 196,800, and the area was 3.14 E minus 2. That's going to be equal to 1.03 times the flow rate of 14 times the velocity on the inlet of 2.242, right? And cosine of 30. It's going to be minus 1.03, whoops, off the page, on here, and 14. And then the velocity at 1. I think I did the wrong numbers right here. Let me try, let me look at this again. Yep, I did it wrong there. I didn't do it wrong on my calculations. I did it wrong just writing the number down. Sorry. This should be 19.83, right? Because it's the outlet right there. And then so this right here should be the 2.242. Once again, I didn't stay within the boundaries of the thing. But this dominates right here. Is that true? Yeah, and I think actually my I think it's something I said incorrectly. Yeah, okay. So the anchoring for I think I think I have it wrong on my page. I think I drew it wrong, to tell you the truth. And I think I said something wrong in class. That's going to make me feel bad. Because this right here is going to be positive when it jumps over onto there, right? Now, why did I make that negative? And that should be positive. Yep, that was an accident right there. Just not thinking today. Yeah. So that's actually going to be the dominant thing right here. It's going to be negative when it jumps over to the other side. Yeah, so I messed something up in class, I think, but I hate it when it happens. Let's see, 3.142, right? E2 minus, and then times, right? So that's going to be 6,000. And this right over here is going to be 19.83, 14 times 1.03 times. Yeah, that's not a whole lot, and then that times the cosine. Boom. So, yeah, so it's going to end up being a negative number right in there. Okay, so, yeah, so I got that right. So a lot of it has to do with how the values just worked out in terms of this, but we're going to end up with a negative force on here, so that's going to be negative 5,968 newtons. Acting onto there. So therefore, 5,968 newtons going that way right there. So we got the thing wrong. And then the y direction, we're going to have ry minus the, I'm not going to do the symbols here. I'll put the values in here because I'm tired. We'll go the elbow first. 343.4 newtons we got from up above. We also have downwards of 58.80. That's the weight of the water inside. And then we have 1.03. And this is coming out. We only have something coming out. There's nothing in the y direction coming in. So we'll have an m dot of 14 and an outlet of 1983. And then we're going to do the sine of 30. Right? So that's only this stuff, and it's only that one coming in, and it's only a certain portion of there. So we get an Ry is equal to 545.2 newtons, and that's up. So I'll rewrite out the other one. Rx is going to be 5,970 newtons to the left. So that is example problem 1. And it's a pretty standard, pretty basic thing. We'll do some more videos. See you soon.